Welcome back. We're going to get started here with what's new in manufacturing solutions. I'm going to turn it over to Cullen Williams, who is going to take us through the next hour. And thanks very much for your guys' attention. Cullen?
All right, thanks, Tony. My name is Cullen Williams, obviously. I'm an application engineer here at CATI. Part of our manufacturing solutions are kind of our hardware side of the business. So we know we've been talking a lot of SolidWorks today, software side of the business. We're going to be taking a look at what we've got in terms of our hardware solutions. So an agenda for today, we're going to take a look at our Stratasys 3D printing solution. So Stratasys, a polymer-based 3D printing technology. We're going to take a look at some of the new machines and materials they have available. Next, we'll talk about metal 3D printing with desktop metal. Follow that up with benchtop milling solutions with Rollin CNC. And finally, we'll cap it off with 3D scanning for reverse engineering and inspection with creaform scanning technologies. So first up, like I said, we'll talk Stratasys. Stratasys has two main 3D printing technologies with polymer, the first one being FDM. FDM stands for Fused Deposition Modeling, and if you've kind of ever heard of 3D printing, you're somewhat familiar with 3D printing, you've probably heard of FDM before. It's one of the oldest, most tried and true 3D printing methodologies out there. So let's take a backtrack and just talk 3D printing in general for a second here. So kind of the workflow and how all 3D printers operate is you have your model that you've created in SolidWorks, right? You have your 3D model. You're going to feed that into whatever 3D printer's print preparation software, and what that print prep software is going to do, it's going to take your model and it's essentially going to slice it in the Z direction vertically and create a bunch of these 2D layers to build up your part in a 3D volume through the Z axis. So where 3D printers differ is the way they go about creating those 2D layers in the physical world. So jumping back into FDM, the way FDM accomplishes this is kind of like we call it a highly precise CNC-controlled hot glue gun, right? So we have a precise heated extruder nozzle, and we're feeding into that thermoplastic filament. And we're able to extrude that very precisely through our 2D layers in order to draw out our geometry layer by layer in the Z height. So that's how we're able to kind of draw out our layers and build up our 3D part volume. Here's a look at some of Stratasys' FDM systems. So you can see on the left here, we've got kind of our desktop entry-level machines with the Mojo and the U-Print. In the middle, we have our office lineup with the F123 series. If you're familiar with the old Dimension series machines, these are the next generation of the Dimension machines. They've improved a lot on the Dimension machines in terms of build volume, build speed, as well as material options. On the Dimension machines, you only had one material ABS. Now on the F-series machines, you have depending on the machine, you have between 3 and 4 materials available to you. Finally, up at the right, we see for our manufacturing shop floor solutions, we have the Fortis lineup. So this is where you get into a lot heavier duty materials, things like polycarbonate, Ultem, carbon fiber materials for FDM prints that really need to stand up to the physical abuse for being used on a shop floor environment for things like tooling and fixturing. So here's a kind of a look at the FDM materials group we have available. Like I said, on our general side of things, we have our ABSs. ABS, if you're not familiar, it's a staple in the thermoplastic injection molding industry. Legos are made out of ABS, just to kind of give you a gauge there. We also have ASA and PLA. From there, we step up into our engineering grade materials. This is where we get into our polycarbonates and our nylon. So we're stepping it up in terms of toughness and strength there, a little bit more from what our general materials were capable of. From there, we move into our high-performance materials. That's where we get into our Ultem resins and our carbon fiber and our PEC materials. So now we're talking extreme heat resistance, extreme stiffness, extreme chemical resistance, things that really need to stand the test of time and abuse on the shop floor environment. And then down here, we'll talk more specifically about this one as well. ST130 is a sacrificial tooling material. More of a niche application, but it does it very, very well. So we're going to kind of talk some of these materials and highlight them individually a little bit more. So first we have ESD Pack. So ESD, that stands for electrostatic discharge. So normally, obviously, plastics are insulators. They can potentially build up a static charge, and where that becomes an issue is if we're trying to house electronic components. Any sensitive electronics, when that static charge builds up, has the potential to damage anything that you're trying to protect with that housing, which obviously defeats the purpose of having the housing in the first place. So with this ESD material, you can safely create electronic enclosures and know that your components are going to be safe from electrostatic discharge. PEC material, if you're familiar with that, excellent chemical resistance and very favorable thermal properties. So the ESD combined with the PEC is a very useful new material we have available. Next up, this is kind of everybody's favorite hot button material currently, is the Nylon 12 CF material. So it's a composite material, the base being Nylon 12, impregnated with carbon fiber filaments. So we're able to lean on the extreme toughness of the Nylon 12 material, and then we get some pretty heavy-duty stiffness with those carbon fiber filaments in order to create a material that has really outperformed by almost 3 times the stiffness of any other 3D printed material previously available through Stratasys. So we're able to print very, very strong, very stiff assemblies, and a lot of customers have seen success replacing even light-grade aluminum parts in assemblies with these printed plastic parts due to the toughness and the stiffness of that we're able to get with the Nylon 12 CF. Up next, we have the ST130 material. So what we're doing here is anywhere we're trying to do any kind of a carbon fiber epoxy wrap and let that cure over our mold tool. Traditional methods, making these molds by hand, it's doable, it's very operator dependent, and it's very hard to get consistent quality results. By printing out, we can see the white there is actually what has come off the printer out of that ST130 material. We'll take that tool, we'll wrap it with our carbon fiber, let that cure. Once that's done curing, we can now very easily and passively soak that tool out, leaving behind what we wanted originally, which was that carbon fiber tubing. So huge help in that sacrificial tooling process to be able to lean on the abilities of additive manufacturing in terms of no or low tooling and very flexible geometries, and to be able to get high quality consistent parts out of that. Ultim 9085 Aerospace Certified. So this is the first Aerospace Certified material, and Stratasys had to go through some pretty rigorous testing, not only for the material properties to be confirmed, but also for the machine making the material and actually printing the parts. So it was originally material that was not aerospace certified. The aerospace industry was very, very interested in it, and so Stratasys therefore chose to jump through these very stringent different certifications required by the industry in order to get this aerospace certified. So there are 3D printed parts available that are being used on different aerospace assemblies today. Next up, we have our newest material, which is Antero 800NA. So it's a PEC-based material, thermoplastic. It is very physically strong, has great mechanical properties. We're not quite as strong as the Nylon 12 CF that I had talked about before, but where we're really shining with the Antero is the super high chemical resistance. So anywhere your plastic parts are going to come into contact with any kind of corrosive chemicals like fuel or hydraulic fluid, anything along those lines, you might want to be looking at this PEC material, as well as the ultra low outgassing. So anywhere where we have very high concerns about outgassing. Where we've seen a lot of interest in this is in space applications for space stations where we have a limited volume of air that we're working with, and we have to be very, very careful about what we bring on board in terms of outgassing because we only have that limited supply of air. So because we're able to have this material with such a low outgassing, the space applications are very excited about that. So I had mentioned that Stratasys has 2 3D printing technologies. We just talked FDM. The second 3D printing technology they have is called PolyJet. Now the way PolyJet works, if you remember from all 3D printing, right, we're slicing things in the Z layer. The way PolyJet goes about building up those layers in the Z height is very similar to how your inkjet printer works at home. We are taking resins out of a print head and we're spraying them onto a build tray. After that build tray has been sprayed, we're passing a UV light over those liquid resins to cure them into a solid. And then the build tray moves down in the Z direction. We repeat the process over and over again, and that's how we're building up our layers in the Z height. What this allows us to do is get very, very fine details like you would expect off your inkjet printer at home. We can get that with a 3D printer. So now we can do different things like mixing materials, get very high resolution prints, full color prints, things along those lines is what we're talking in terms of PolyJet. Different PolyJet systems currently offered. So again, kind of same theme here. On our left, we have our entry-level machines with the Objet 30 Pro and Prime. These are just single material machines, so you are able to get very high resolution prints, but you're only going to be printing in black or white or blue, one at a time. In the middle, we have kind of our office engineering grade Objet Eden and Connex. So these are 2 to 3 material machines. We can start getting into the material mixing realm, but we're not full color yet. Once we get up to the Stratasys J750, J735, that's when we get to our full color capability. We have a full CMYK palette as well as clear and different rubber-like materials, and then we can incorporate all into the same print. So now we can get prints that have not only have a full color spectrum on there, but include real touch, real feel, rubber-like textures, clear, all different kinds of things to create very photorealistic parts, very good for industrial designers, people trying to make end-use prototypes to get a very nice mock-up of what they're trying to do. Here's a look at our PolyJet materials. So on the left for our general, this is where we're just going to have our base colors, like I mentioned before, CMYK, white, clear, things along that line. I mentioned our flexible materials. So we have Tango and Agilis. These are our rubber simulations. And then we also have specialty medical. So we have dental materials, VeroFlex hearing aid materials, things along this line that really benefit from the high resolution and high fidelity of PolyJet systems. So touching a little bit more detail on the Agilis 30. So if you're familiar with Tango, Tango was kind of our old rubber simulation material. Consider Agilis Tango 2.0. It's the upgraded version. So a lot more tear resistance, a lot more elongation for break, just a better simulation for your rubber applications than Tango was able to do in the past. We also have a new lineup of vivid colors that is in the process of being released. So the original Vero colors, Vero Cyan, Vero Magenta, Vero Yellow, things along this nature had an opaque base to them. And what this means is one of the things upgraded between the old material to the vivid material was that when you're trying to mix too many colors together, the fact that there was that opaque base there kind of muddied the colors and made it very difficult to get very, very fine control over the color palette that you were able to print. By switching over to a transparent base instead of an opaque base, the new Vivid Vero color family is able to have a lot finer control and expand the color gamut of the machine quite significantly. So we currently have Vivid Magenta and Vivid Yellow out. Vivid Cyan is on its way, and we are on our way to expanding our color palette from 360,000 colors upwards towards 500,000 colors. So off of a printer in one print, we can potentially print 500,000 different colors. GrabCAD Voxel Print. So this is a software-controlled process, and what Voxel Print is, so a voxel is a volumetric pixel. So think pixels on your TV screen, right? You've got a length and a width to them. Now a voxel has a depth to that as well. And what a voxel translates to in terms of PolyJet printing, that's the smallest droplet that we can control and print at a time. So with voxel printing, we can potentially control every single droplet independently within the print. You can see here, obviously, we've got this bust of Nefertiti with an over-dramatized voxelation of it. Obviously, we're going to be a lot more finer with the PolyJet technology. This is very useful for artistic things like this, or as well as controlling the internals for medical models and mechanical models. So how voxel printing essentially works is, if you can imagine, if you have 1,000 progressive slices like below, you can stack them together as they change through space and create a very, very unique, interesting model here as we're controlling the internals very tightly through voxel printing. So like I mentioned, we have very high use in the medical industry where we want to control that internal geometry and make it exactly how we were looking to get it, as opposed to just a kind of a color wrap around the outside. Now we're able to control that internal geometry very, very tightly. Additionally, a great use case for voxel printing is Leica Studios. If you've ever seen the movie Box Trolls or Coraline is in their portfolio. Leica Printing originally came to PolyJet. They really liked the technology, but their one complaint was the eyes. They weren't able to get the eyes as lifelike as they needed to, and something that was very, very important to them, a complaint was zombie-like or dead-looking eyes. So by being able to use voxel printing, they're able to give their eyes much more depth, much more color, and give them that lifelike ability that they were looking for to make it, for their films, a lot more believable of a character. So Leica is a huge proponent of voxel printing and uses it constantly. So what they'll actually do is they'll print out all the faces and different actions of their characters and use those for their stop motion animation films, as opposed to what they were doing before by hand. So it speeds up their process a lot more. So next we'll talk desktop metal. Desktop metal is a fully end-to-end system for metal prototyping. So this is all office contained. It's a three-part system. What we see on the screen there, and I'll go into more depth on this process in following slides, but we have the printer in the middle, operates very similar to an FDM machine. Then we have a debinding station, essentially a post-processing station, and from there we move to the sintering oven on the right. One of the most exciting things about the desktop metal system is that it's about 10 times cheaper than traditional powder bed fusion systems. So we can see the comparison between powder bed fusion and the DM Studio system there. So if we're just looking for metal prototypes in the office, DM Studio system is a great economical way to get started down that path. So again, the idea behind this system is office friendly. We want it as office friendly as possible. We don't want metallurgists on staff. We don't want to have hazmat suits in order to operate our equipment. We want to be able to get parts very, very quickly. Here's a high overview of the process. So we start with bars of feedstock, and what these feedstock is comprised of is about 80% metal powder, 20% polymer binder. And what that allows us to do is we feed that again into, like I said, an FDM style print head, so a nozzle, a heated extrusion nozzle, is we melt the plastic and flow the metal powder out. So we're nowhere near metal melting temperatures at this point. We're just melting that plastic and using that plastic as a vehicle of transport to flow that powder out and create our print. So then we get all the benefits of 3D printing. We don't have tooling. We don't have long setup times. We don't have long programming times. We can just get that nice flexibility of 3D printing in a metal environment. From there, we move to our debind, which is a liquid debind bath, and what that does is it soaks out our polymer binder. We don't want that polymer binder in there because when we move to our sintering process, it's going to really screw with our metallurgical properties and it's going to make for a large mess. So we really want to get that polymer out of there in the debind phase, and then from there, we move into the sintering phase, and that's when we heat the semi-metal object up to just below its melting point, and then those particles coalesce together and create a fully dense metal part. So here's a closer look at the Studio System printer. So like I've been saying the whole time, very similar to FDM, very familiar design guidelines, and the biggest selling point, in my opinion, is the office-safe material. So normally for metal 3D printing, you're dealing with metal powders. So those can get in the air. Like I said, you have to have a hazmat suit. If you inhale any of that, that's a very, very serious offense happening, and you really don't want to be handling that powder. So in order to be office-safe, they went with the metal rod design. So you can see the build area about 12 by 12 by 8, or 12 by 8 by 8, excuse me. We can get down to 50 micron resolutions, and you can see we're about a cubic inch per hour, which is very similar to current FDM speeds. Here's a look at the material swapping process. So again, in powder-based systems, when you want to switch over from 17.4 to 4140, you have to clean that machine out, you have to vacuum that out, and make sure you get every particle of that old material out of there to make sure that it doesn't mess with your mechanical properties of what you're trying to print in the new material. For the Studio system, all that's required for a material change is swapping in and swapping out those cartridges. So there's no, like I've been saying this whole time, there's no hazmat suit. You don't need to vacuum out any kind of metal powder or anything like that. It's a very quick and easy click in, click out material swap. So here's a look at the printer running. So we can see it moving around, printing our part out. We've finished the print. This is just a propeller print. From here, the material is almost clay-like. So I said 80% metal powder, 20% polymer binder. It's nowhere near metal at this point. If you drop it on the ground, it's going to break. But what that allows us to do, some of the nice features that we can do a lot of hand finishing in this stage. So we can go up and we can take some very, very fine sandpaper and just make some of those surfaces a lot nicer before we're in that metal state where it's a little bit harder to get that nice surface finish on there. From there, we move to our debinder. We soak out that polymer binder. And then we move on to our sintering furnace. So we heat it up and we get our fully dense metal part. A nice feature of the desktop metal system as well is, if you can see on the left there, that's the support structure for a powder bed fusion. On the right, we can see a video of someone removing the supports from a bound metal deposition process, which is the DM Studio process. So the DM Studio system will actually print everywhere in between where supports and model touch. It will print an interface layer of ceramic material. And what that allows us to do, as we just saw in the video, is just by hand pop away our supports. So it's very nice to be able to do that. Again, whole theme of office friendly. We really don't want to have a bandsaw to remove parts from the powder bed fusion on the left, or angle grinder or anything like that in an office environment. We really just want to be able to pop it off by hand and move forward from there. Here we have Desktop Metal's production system. So we were just talking about the Studio system, which was focused on prototyping, small batch runs, things like that. The production system is metal 3D printing at scale.
Metal 3D printing could change much of the world around us if it was fast enough and cheap enough for mass production. Introducing the production system, powered by single-pass jetting. At up to 100 times faster than laser-based systems, it's the first metal 3D printing solution for mass production. It works by combining 2 powder spreaders and 1 print unit into a single pass system to both spread metal powder and print. Unlike existing metal 3D printing, there is no wasted motion with single pass jetting. A single pass starts in the powder spreader, where a metering system deposits metal powder, and a compacting system forms a layer as thin as a human hair. The print bar follows, jetting droplets of a binding agent. Millions are jetted per second, binding metal powder to form high-resolution layers. Anti-sintering agents are then deposited, making it possible for supports to fall off after sintering, saving hours of post-processing. Once the layer is dried, the process repeats itself. Single-pass jetting is bidirectional. We combined all the necessary steps for printing into a single pass, so that whenever there is movement, there is printing. This makes it possible to print parts in minutes instead of hours. Once printed, the brown parts are heated to just below their melting point. Binder is removed, and metal particles are fused to form a dense solid. The production system is cloud connected. Sophisticated software manages the entire workflow with profiles that are tuned to every build and material, from the printer to the furnace, delivering dense metal parts. The result is sheer throughput. In the time it takes laser-based processes to produce just 12 impellers, desktop metal single-pass jetting technology would have produced over 500. To date, metal 3D printing has been too expensive and too slow to change the world around us. At up to 100 times faster than existing technologies, the production system unlocks the cost per part needed for mass production. For the first time, it's possible to go to market with metal 3D printing.
So I think that's a pretty cool video. It shows really the potential for this for mass production. If you remember from the previous slides, I had mentioned that current FDM technologies are at about 1 cubic inch per hour. This technology is slated for about 500 cubic inches per hour, so significantly faster for that mass production environment. Next up, we'll talk Rollin CNC milling machine. So we've been talking additive, jump over to subtractive for a little bit. So what are the advantages of a Rollin CNC? Why subtractive over additive? One of the things that Rollin does really well is it fits in your office, home, or classroom environment. They're very good at dust control, things like that. Additionally, it's all designed around ease of use. So it comes with a free SRP player software. The nice thing about this software is if you have people on staff who really aren't familiar with CNC programming, really aren't machinists by trade, they're more design engineers, things along that nature, the free SRP player software really makes the transition to start using this equipment very, very easy. Now, that being said, if you do have someone on staff who's familiar with writing G-code, making machine tool programs, the SRP player software has that functionality built in. So it's kind of as much help as you need or as much functionality as you want to get out of it. The MDX50, kind of the mid-level grade milling machine. You can see our process area about 16 by 12 by 6. It comes standard with an automatic tool changer and is run off of RML NC G-code, and we have an optional rotary 4th axis on there. So a lot of functionality in a smaller package is very, very nice to have. MDX 540, a little bit larger process area, about 19 by 15 by 6. 4-position automatic tool changer again as well, with additionally an optional rotary 4th axis. So what this machine can do, the MDX50, we're going to be doing materials like foams, plastics, woods, things along this nature. With the MDX 540, we're able to start getting into things like aluminum and brass. Anything that's a non-ferrous metal, we're able to cut with the MDX 540. CNCs have a superior form, fit, and finish. They can hold very, very tight tolerances with a CNC, create exact and stable form parts, snap fit parts, things along this nature, and really hold very, very tight tolerances. Case study on just a comparison of an example part here. So we have a fixturing prototype. We can see the cost for material, labor rate, or internal cost around $50, right? We job that out, get that quoted at $375. You can see right there the numbers in terms of dollars, what we're talking in savings. The dollar savings are always nice, but in my opinion, the thing that is even better about a solution like this, and this even applies to both 3D printing and CNC milling, is the time savings. You can see here part build time, 4.2 hours. I would like to see a job shop that would get you that back in more than a couple of days without a rush charge on there. So we can get that back. We can come in the morning, want to test out this prototype, set it on the mill, and by lunchtime we can go out on the floor, test this prototype, and see what we're trying to do with it, make our tweaks, whereas before our entire process is just lengthened by waiting and waiting and waiting on these job shops. So bringing that process in-house really helps speed things up. Comparison of CNC versus 3D printing. So 3D printing is really good for complex inorganic shapes. Not all parts need to be optimized. So here for a CNC we see a very blocky part. This is actually a project I did, a fixturing of a 3D printed part. This part was actually milled out of foam, and so this is something that we could definitely 3D print. I mean, you load that up in the printer and it's going to chug away and it's going to give you a part, but such basic geometry may be a better candidate for milling. Here you can see cost differences can be big for large, bulky parts. So here's a comparison of a couple of different, our PolyJet, our FDM, and then our MDX 50. So you can see for yourself, PolyJet's going to take a long time. We're going to get a really, really nice fine surface finish on that, but we're going to take around 9 hours to do it and $100 in material. FDM, we're a little bit faster. We're able to do it in a thermoplastic, which is nice, but $30 versus our $3 worth of machine foam, and we can have this cut on the mill in about 4 minutes. So this is an optimized program. Like I said, I designed this fixture with the idea of throwing it on the mill. I used it all with the same tools, so we didn't have to go through any tool changes. This was really one where I was trying to crank this out as fast as possible, and that's something that you can do with the milling, is have a little bit more control over that and go through something very, very quickly. So the entire project behind this particular fixture, the idea was, how do we incorporate additive and subtractive together? How do we lean on the strengths from both of those technologies to create something entirely new? So one thing from 3D printing is that we're always trying to keep in mind our print orientation. If you remember, we're slicing parts in the Z height, right? What that translates to is it's often a trade-off between surface finish, part strength, fidelity of different features. Sometimes you have to make a choice of, these features are more important to me than these. I'll get nicer resolution on these versus these other ones over here may not be optimal for the print orientation I've chosen. So what you can see on the print here, or on the screen, excuse me, is just a dome, just a very basic dome, and it's showing that on vertical walls for 3D printers you're getting a very nice surface finish, and on the top you're getting what we call stair stepping. So again, we're building in layers, and those layers have a finite thickness, so at a certain point we're going to layer out and create this stair-step effect over more horizontal curvature. Also, very small holes on a 3D printer can be somewhat challenging. And again, going along that theme of we're kind of having to choose between strength or aesthetics sometimes. So what we can do with our mill is we can do different surfacing operations and different boring operations to drill out holes and finish surfaces a lot nicer and still get that flexibility of the 3D printer. So this was just essentially just a test to see what kind of surface finish we would get best based on depth of cut. You can see on the left, again, was that dome straight off of the 3D printer where we have our stair stepping on the top of the part. On the right is the part in that foam fixture that I had cut out on the mill, and then actually ran a milling program on the surface of that dome. And it's actually, if you were to look at the top of the part, it's actually a helical cut where at 0 degrees was a 0 depth of cut, and then as you go around it ramps up to a full, it was actually a 26,000th depth of cut. So it was just for a project for me to see about where, in terms of 3D printed layer height depth, do we want to cut our finished parts to make them have the nicest surface finish. So you can see there what the kind of surface finish that we're able to get off of a FDM part, combining it with the Rollin mill. Next up, let's talk 3D scanners with Creaform. So these are very, very powerful tools in terms of reverse engineering and inspection applications. So we can see across the top here, we have our lineup of different hand scanning solutions with the GoScan, Handyscan, and Metroscan. We also have a portable optical CMM option with our Handyprobe. So now we're grabbing single point data as opposed to surface data like with the hand scanners, but we're grabbing that single point data very, very accurately. Finally, we have our Macshot 3D, which is a photogrammetry system. If you're not familiar with photogrammetry, the basic idea is we're taking a bunch of 2D photographs and we're using references within those photographs to stitch those together and create a 3D volume. And what that allows us to do is to create 3D measurements within that 3D volume and take very, very precise measurements over very, very large volumes. We see this a lot in the aerospace industry where someone wants to measure maybe tip to tail on a 747, and we can hold that within a few microns of accuracy over such a long distance. So first up, we'll talk GhostCAN. The GhostCAN 3D, it's our kind of our entry-level white light-based scanning solution. White light scanners, they're easy, they're fast, they can pick up colors and textures. They're a very nice introduction to the scanning environment. So taking a step back, we're talking in terms of general scanners. What two pieces of information do scanners need to operate? The first one is the scanner obviously needs the surface of your part. The way that the GhostCAN acquires that information, it projects that square that we can see on the seat there. It actually almost looks like a QR code. The scanner knows what that QR code is supposed to look like on a perfectly flat surface, and then it looks at what it's currently seeing, and it can use the difference between those two known things to create the 3D surface of our part. That's the first piece of information the scanners need. The second piece of information is where to put that surface. Now we've created this nice square of surface data. Where do I put that relative to the rest of my data? We need to be able to trace ourselves back to our origin and essentially leave a trail of breadcrumbs as we work our way across our part to be able to stitch all of our data together. So how does the GhostCAN go about creating this trail of breadcrumbs so that we can get usable scan data off of this? It's a system they call intelligent hybrid positioning. The first methodology it can use is with geometry. So think facial recognition. The scanner is recognizing possibly the seams in that seat. As I move my hand along, a couple of degrees to the right, couple of degrees to the right, the scanner is saying, hey, I recognize those seams, I know where I am, I've moved a couple of degrees to the right. So we can use unique geometry on the surface of the part to create our reference frame around that part. The second way, as I mentioned, the white light scanners can pick up colors. So anywhere there is a color differential on the surface of our part, we can pick that up and use that as a reference frame as well. So we can continue across the surface of the part even though it's flat as long as it has some sort of color differentiation. Anywhere on our part that doesn't have unique features, that doesn't have unique color differentiation like the back of this seat, we would essentially be lost if we didn't have these, we'll call them man-made reference targets. We have little positioning target stickers that you can add onto your part, and again, the scanner knows what those look like, recognizes that as a reference target, and we can continue to chain our reference frame across the entire surface of the part. So now we're able to use geometry, colors, as well as the positioning target stickers to create a full reference frame around our part and get all the scan data that we need. So we have two models of GhostCAN. There's the GhostCAN 50 and the GhostCAN 20. So before we get into this, I want to talk the difference between resolution and accuracy. We see both of those numbers up there. What resolution, or let's talk accuracy first. So you can imagine you've got a flat plane, that's your nominal perfect plane, right? What the scanner is doing is it's constantly creating points along that surface of the plane, and there's always going to be some sort of small error involved where it places those points. What accuracy means is how close to that surface are those points that the scanner has created. So with the GhostCANs, we're able to create points with an accuracy of plus or minus 4/1000ths of an inch. So all our points are going to be within 4/1000ths of an inch plus or minus of that true nominal surface. What resolution is how dense are those points packed on the surface. So same thing of like resolution on your TV screen. Again, the more pixels you have on your TV screen, the more finer detail you can capture. Same thing with the scanners. So if you have a feature that's too small, that's lower than the resolution of the scanner won't be able to pick that up because it doesn't have enough point density to be able to create that feature. Now, if we have a good resolution compared to our feature, we'll get a nice crisp feature on the surface of that part. So what resolution comes into is minimum feature size that we can accurately scan. What accuracy comes into is what are your tolerances? What tolerance requirements do you have for your part? Getting back specifically to the GhostCANs, so we can see here, now that we know about resolution and accuracy, that the GhostCAN 50 has a lower resolution, and then the GhostCAN 20 has a little bit higher resolution. So the GhostCAN 50 has a much larger scanning area than the GhostCAN 20, about 15 inches by 15 inches for the 50, and about 4 inches by 5 inches for the GhostCAN 20. So what we generally recommend is the GhostCAN 50 is for larger parts at kind of a lower or more rough resolution, where the GhostCAN 20 is for smaller parts where you need a higher resolution. Now, that being said, we can always use scanners for different applications. They just may not be the best tool in your tool belt for that. We could use a GhostCAN 20 to scan up a larger part. It's just going to take a lot longer to work your way across that surface with that smaller scanning area than the GhostCAN 50 would, if that makes sense. Next up, we'll talk to Handyscan. So the Handyscan is a laser-based scanning solution, and it's also a metrology-grade scanner. So we see this scanner used with success a lot in quality control applications, and that's because the scanner has such high accuracy and it actually comes NIST certified. So a lot of times customers want to see that NIST certification and actually need that NIST certification in order to be able to use a new piece of equipment for their QC applications. So we can see on the screen here, it's a very portable technology. We can see we've got this guy, he's out on the shop floor. All he has is his laptop with him and a cord going from that to the scanner, and we're able to scan up parts on the shop floor. So we're not constrained to granite countertops bolted down to fixtures in a nice $1 million QC lab. We can actually bring this down onto the shop floor and again, speed up this process. This is all about getting our results more accurate and more quickly, right? So a bunch of different industrial applications here with the scanners. So we have different concept design. Tooling design is a great one. So you can take scans of your tooling, overlay it onto your CAD model to make sure that the guys in the tool shop made everything correctly, or the job shop that you sent it out made everything correctly, and see differentials there. QC, again, very, very big. So we're taking scans of our parts and we're overlaying those onto the CAD models of those parts and using that CAD model as the nominal and spitting out a report that says, hey, out of your 500 measurements, these 10 are out of spec and here's how far out of spec they are. So really speeds up that process, whereas with like a CMM, each of those 500 points, you have to measure those one at a time. So you're going through that serial process. Whereas with scanning, as soon as we're done scanning the part, we feed that scan mesh to the program and it spits out our measurements very, very quickly. So we're going through our inspection process a lot faster. Always good for reverse engineering and aftermarket equipment. So if you can't get the CAD from the OEM, they don't want to give it out for whatever reason, it's very nice to be able to have that part on your desk, scan it up, use that in SolidWorks as reference to create your part that's going to then mate up to that part, and that's your final product. Very, very useful there. Maintenance, repair, and overhaul. So now we can take scans of tooling and different machines. Let's say we get a tool in, a mold in, we scan it up on day one and we save that. That's our day one scan, right? Now we're going to run it for 6 months. We're going to scan it up again. We're going to overlay those scans. We're going to see where our tool is wearing out. Now we're going to scan it up at 12 months, so an extra 6 months down the line, and do that same overlay process. Now we have 3 data points throughout time, and we can see as our tool is wearing out, and we can predict, hey, it looks like at 36 months, our tool is going to wear out past what we deem to be acceptable. So now we can mark that date on our calendar, and maybe that tool has a 2-month lead time. We can be ahead of the game, as opposed to QC comes and flags the tool and says this tool is making bad parts. Now everybody's trying to get a tool here tomorrow. That takes 2 months to make. So having that ability to be proactive rather than reactive, we've seen a lot of success there. So a little bit about how the Handyscan operates. So the Handyscan is a laser-based system, whereas the GhostCAN from before was a white light-based system. A couple of key differences there. The lasers can't pick up color, and they can't pick up the unique geometry on the surface of the part. If you remember, we always have to have a trail of breadcrumbs back to our origin. So the way that this Handyscan achieves that is with those positioning targets. So we put the positioning targets on our part, and from there we can build our reference frame, and then the scanner will recognize the targets, create our origin, and then we can scan across the surface of the part. So we have 2 models of Handyscan, the 300 and the 700. Again, looking at our resolution and our accuracy numbers here. So we're about 100 micron resolution for the 300 and 50 micron resolution for the 700. Accuracy is 1.6 thou versus 1.2 thou versus the 4 thou for the GhostCAN. So we're getting a lot tighter here, and this kind of plays into that NIST certification as well. Key differences as well between the 300 and the 700. If you saw on the last slide, it's a little bit difficult to see here, but I am going to be doing a live scan at the back at the end of the presentation that you'll be able to see more clearly. It projects kind of a crisscross pattern of lasers on the surface of the part. The 300 has 3 laser lines that crisscross, the 700 has 7. So obviously we've got a little bit larger of a scanning area, more data being acquired with the 700 per second. Additionally, the 700 has what's called a single laser mode. So instead of a crisscross pattern of lasers, you can swap to a mode where we're just shooting a single laser line. And what that's very, very useful for is getting down into nooks and crannies and crevices and things like that. All of these scanners are vision-based systems. The white light, the laser, all of it is dependent on some sort of light and some sort of camera system feeding back in that data from that light. So what I always say is if you can't see it, you can't scan it. And where this ties into with the single laser mode is getting down into bores. If that bore is too tight in terms of the focal length of our scanning lenses, it's very difficult to get down into without that single laser mode. So that's why that single laser mode is very, very useful if you know you're going to be looking for hole measurements and things along that nature. Next up, we have the Metroscan. So the Metroscan is going to be a very similar in terms of accuracies to the Handyscan, but where it's going to shine and outshine the Handyscan is larger volume scans. So Handyscan, you want to scan up an entire car and get that entire mesh is going to be able to hold that accuracy much tighter over that larger volume than the Handyscan or the GhostCAN would be able to. The Metroscan is a 2-part system, and this is kind of the secret sauce of how we're able to hold that accuracy over such a large volume. So on the left, we can see we have the C-Track, which is this camera system that will stay in the background watching you as you scan with the hand scanner. And if you notice now, Metroscan on the right, the positioning targets are actually in a cage around the hand scanner. So the C-Track recognizes those positioning targets that are in your hand, and that's how we create our reference frame. So now our reference frame is stationary with the C-Track, and we don't have that error buildup as we're hopping reference frames like we do with the other scanners over the volumetric accuracy. So here we can see it being used on the shop floor. We've got a car body. You can see in the foreground we've got the C-Track, and then we've got our employee here with the hand scanner scanning up the car body. Where this is really useful is inspection applications. So again, that part to CAD analysis, first article inspection, supplier product quality inspection, very useful for tooling certifications. What this photo is showing you, it's a very unique application to the Metroscan. It's actually the only scanner on the market that can scan highly reflective parts. So again, all these scanners are vision-based scanners. There are 3 categories of parts that can potentially cause an issue, and those are clear parts, very dark parts, or shiny parts. And so all of those, in one way or another, will affect the laser quality bouncing back into the camera. So the Metroscan does a very, very good job of being able to scan highly reflective parts by utilizing the C-Track as a third reference. So you can see different accuracies and volumetric accuracy numbers here for the Metroscan, different models, 350, 350 Elite, all the way up to the 750 Elite. And again, we can see the accuracies are very similar to the Handyscan down to 1.2 thou. Next up, we have the Handyprobe. So again, this is now, instead of surface data, we're grabbing probe point data, but we're doing it very, very accurately. So again, you can see we've got targets on the probe, and you can guess, yes, the C-Track is involved in this process as well. Where this really shines is where we have large parts, and we really need that flexibility where they're not fitting onto the bed of our CMM, or we want to be able to go out to the shop floor and do this very quickly and not haul this big part into the quality control lab and try to figure something out. We can just go out and do this very flexibly with the Handyprobe system. So you can see same part. We've got the C-Track in the foreground again, and now we're probing points with that wireless probe. 2 models of Handyprobe, the Handyprobe Next and the Next Elite. Now we're able to get down to 8/10 thou accuracy with that Next Elite versus the 1.2 of the Metra and the Handy. Finally, let's talk Macshot 3D. This is for very, very large parts. Like I mentioned, aerospace likes this a lot for very large distance measurements. So we're taking 2D photographs, stitching them together to create a 3D volume and grab 3D measurements from that volume. So really the minimum size that we're trying to take measurements off of is 6 feet, and we really just go up from there. Really, really strong volumetric accuracy with the most uniform error distribution of any of our scanning or metrology options available. So you can see here we're taking photographs of the interior of an airplane. different accuracy and performance numbers here. So now we're significantly tighter. So, and I almost always get tighter than these numbers. These are just the worst case scenario numbers. But we're getting into the couple of micron levels of accuracy with this photogrammetry system. Now again, we're not grabbing surface data, we're grabbing point-to-point measurements, but we're doing it extremely accurately with this system. A success story utilizing a good portion of the scanning technologies available through Creaform. So Jet Aviation, a team of Creaform application engineers, reverse engineered a Boeing 737. This was a project that they had originally predicted to take 3.5 years with a cost of $2.3 million to be able to get a CAD model of this aircraft interior. Creaform was able to complete it in 4.5 months. So 4.5 months versus 3.5 years. You can really see how these hand scanners are really speeding up people's workflows in these reverse engineering applications. So we're able to grab a whole, very accurate look at these interiors, whereas before we're taking hand measurements, things along those natures, which are not only inaccurate, but very time consuming. So now I'm going to switch over to a live scan demonstration. I have a demo part up here, and we're going to be able to see the scanners work in action. Are you still up here? Good. Okay. So what I have brought up, this software is called VX Elements. It's Creaform's brand of scanning software. So we have a couple of different modules, a module for reverse engineering, a module for inspection. That being said, the scanners are software independent. So they will work with other softwares that accept scanners as well. So if you have something like Geomagic Design X or Polyworks, the scanners will work with that as well. So here I have my demo part. As you can see, I've got all my positioning targets pre-placed on here. And again, what this is going to allow me to do is create a reference frame around my targets, around my part, to make sure that I can accurately place my scanning data. So I'm just going to start up the scan here. It's a very simple process. And all I'm going to do is I'm going to hit the button on the back of the scanner, and we're going to see those laser lines that I had talked about being projected onto the part. And then we're going to start to grab the surface of the part. So you can see this is all real time, happens very quickly. I'm just going to paint across the surface of the part. The reason that I can do this while in the air is because my reference frame is only relative to my targets. The scanner doesn't know if the part is moving or if the scanner is moving. All it knows is that it's moving relative to the targets. This is pretty cool for demo uses. It gets some nice oohs and ahs. But where it's really useful is out on the shop floor, where you're trying to take measurements and the guy with the forklift goes by at 20 miles an hour behind you, or you have big stamping pieces of equipment that are causing some serious vibrations and potentially ruining other forms of measurement. This form of measurement is really independent of that vibration, because obviously you can see some pretty big vibrations happening right now, and I'm still able to very accurately scan my part. So you can see from here, we can go into all different applications. We can go into VX Model, which is the reverse engineering application. We're going to be taking different entities off the surface of the part, porting them into SolidWorks, and using those as reference for our CAD model as we build up our SolidWorks model. Or we can go into VX Inspect, which is for quality control, and that's how we're going to take a scan mesh and a CAD and overlay those and take measurements off of both of them. So what we're able to do then is, like I said before, take very large amounts of measurements very accurately and very quickly. So with that, I'm going to wrap up my presentation. If anyone is more interested in the VX Model Reverse Engineering or the VX Inspect Inspection program, we're out at the booth out front, and I can go through some specifics with you there. But from there, I want to thank everyone for coming out, and if you have any questions, please feel free to stop by the booth up front. Thank you.